Welcome to AudioCert, where the official study guides are brought to life. In our digital age, data isn't just everywhere. It's often cleverly hidden, fragmented, or, sometimes deliberately obscured. For anyone in digital forensics, understanding where every byte actually lives, from the physical spin of a platter to the invisible structures of file systems, well, it's absolutely non-negotiable. Today, we're taking a deep dive into the foundational landscape of systems, disks, and media. This is the very bedrock for uncovering digital evidence. And this is absolutely critical knowledge for anyone pursuing the EC Council Computer Hacking Forensic Investigator certification, specifically for Chapter 2. It's really about building that forensic muscle memory, understanding the digital terrain so intimately that no piece of evidence can hide.
It truly is, yeah.
Yeah.
Without a solid grasp of this chapter, an investigator is, well, essentially operating blind. We're talking about the core mechanics that dictate not only where every byte of data resides, but how it's accessed, and critically, how it might be recovered even when a user thinks it's irrevocably gone. It's the groundwork for every subsequent step in digital forensics. And the ability to navigate these foundational elements is what ultimately separates a novice from a truly skilled professional. We're aiming to give you those aha moments, the ones that make the theory click into practical, actionable insight.
I couldn't agree more. And to really get well informed on this, we'll journey from the physical hardware that stores our data right down to the invisible structures of file systems that organize it. And then we'll expand our view to the vast array of other digital devices that hold potential evidence. It's a comprehensive look at the digital landscape that any aspiring computer hacking forensic investigator really needs to understand inside and out. So let's get started. Hashtag deep dive discussion. Okay, when we talk about digital storage, the first thing that almost always springs to mind is the hard disk. It's kind of the backbone of most computers. But what exactly is a hard disk drive, or HDD, and what makes it so central to our digital lives, especially, from a forensic perspective?
Right. At its core, a hard disk drive is a non-volatile storage device. Now, non-volatile is a really key term here. It means it's physical media that retains data without needing electrical power. So you can power down your computer, unplug it, leave it for weeks, and the data on that hard disk remains exactly where it was. This makes it ideal for, well, permanent information storage. HDDs write digital data as incredibly precise magnetic patterns onto rigid, spinning platters housed inside the drive. Because they're typically installed directly into a computer, they offer significantly faster access and processing speeds compared to, say, older removable media like floppy disks or even mini flash drives for sheer throughput. And it's not just traditional PCs anymore, right? You find hard disks today in everything from camcorders and game systems like the original Xbox to digital video recorders. For a forensic investigator, that non-volatile nature means data is preserved, even if the power is cut, which is just fundamental to evidence integrity.
That makes perfect sense. Yeah, the data sticks around. But when you look at all the devices around us today, from desktops to tiny laptops, it's clear that one size fits all simply doesn't apply to hard drives, does it? How have these physical dimensions evolved?
Not at all. The physical external dimensions and interfaces, which we collectively call form factors, have evolved quite a bit over the decades to fit different needs. The earliest PC drives, appearing around the 1980s, were the 5.25-inch form factor. These were quite bulky, designed to fit into the same bays as the 5.25-inch floppy drives at the time. You rarely see them now. They're largely obsolete. They were quickly succeeded, back in 1983, by the 3.5-inch drives. These became, and largely still are, the common size for modern desktop PCs. It's a bit of an interesting historical note, actually, that a 2.5-inch drive is closer to 4 inches wide, but it was named because it fit into the 3.5-inch floppy drive bay. Funny, huh?
Oh, I didn't know that.
Then you have the 2.5-inch form factor, which is the standard for laptops and notebooks, offering a much more compact solution for portable computing. All these sizes share a common design philosophy. They encase their delicate internal mechanisms within a sturdy metal case, primarily to protect against dust and other foreign elements. And we'll get into why that's so critical in a moment.
Okay, so once you have the right physical size drive, how does it actually talk to the computer? What are the key external components that allow it to receive power and communicate? And how do they determine its role in the system?
That's where the external components come into play, specifically the connections. For a typical 3.5-inch hard disk, you'd find three main interaction points. First, we have jumpers. These are small electrical connectors that essentially act as on-off switches, configuring the hard disk for its role in the system. Historically, you'd use them to set a drive as a master or a slave. The master drive would be the primary hard disk, usually the one with the operating system, accessed first during boot up. A slave drive was a secondary disk used for additional storage. It's worth noting, just for clarity, that in many modern materials and exams, these terms are now commonly referred to as primary and secondary to reflect, evolving language standards.
Right, primary and secondary, got it.
Second, there's the power connector, which links the hard disk to the computer's power supply, giving it the electricity it needs to spin its platters and operate its electronics. And third, the hard disk interface. This is the communication channel, the actual port and cable that allows the drive to exchange data with the motherboard. For example, older systems often used an integrated drive electronics, or IDE, interface, which connected via a thin, flat ribbon cable. We'll dive much deeper into these interfaces later as they fundamentally define how data actually flows and is accessed.
It's amazing how much technology is packed into these drives. You mentioned they're sealed for protection, which makes me think of the incredibly delicate internal mechanisms. What truly happens at a microscopic level inside, and what makes it so fragile?
This is where the true engineering marvel, and indeed the fragility, becomes apparent. Inside that sealed, dust-free case, you'll find one to several rigid, round discs called platters, stacked precisely on a central spindle. These platters are typically made of aluminum alloy, glass, or composite, and are coated with a magnetic substance. A motor spins this spindle at incredibly high RPMs, revolutions per minute. We're talking thousands for older IDE drives, often 7,200 or even 15,000 RPMs for modern drives, creating a cushion of air for the heads. Data is then written to and read from these spinning platters by tiny electromagnetic read-write heads. Each side of a platter usually has its own head.
Okay, so heads for each side.
Exactly. Now, the organization of data on these platters is crucial. Data is recorded in concentric circles called tracks. Imagine them like the rings on a tree trunk, or maybe very fine grooves on a vinyl record, but perfectly circular and distinct. A single 3.5-inch disc can have thousands of tracks, typically numbered from 0 at the outermost edge to around a 1023 nearest the center. These tracks are further divided into smaller physical storage units called sectors. A sector is a segment of a track, much like a slice of a pie. And they're almost universally 512 bytes or 0.5 kilobytes in size. Knowing the precise track and sector number allows the computer to directly locate any specific piece of data on the disk.
Wow, that's precise.
It really is. And this foundational physical layout, the tracks and sectors, is established during a process called low-level formatting, LLF, which is typically done at the factory. It's absolutely essential because it creates the magnetic landmarks on the platters that the disk controller needs to begin writing data before the operating system even steps in for higher-level formatting. Now, for that truly mind-boggling insight, the read-write head doesn't actually touch the platter. It floats an astonishingly tiny distance above the platter surface, less than 0.1 microns.
Less than 0.1 microns, that's tiny.
It's unbelievably small. To put that in perspective, an average dust particle is about 2.5 microns, and a human hair is around 50 microns thick. So the head is flying over the platter closer than a dust mote. This explains why hard drives are sealed so tightly in a clean room environment. Even a microscopic piece of dust or a stray hair could cause the head to collide with the platter's surface, known as a head crash. That results in catastrophic data loss and physical damage to the media. Yeah. For forensic investigators, understanding this fragility underscores the importance of proper handling and, clean room procedures for damaged drives.
Even with all that precision in the sealed environment, things can still go wrong over time, right? What happens when a part of this intricate system is physically damaged or simply wears out, making a section of the disk unusable?
That's when we encounter bad sectors. These are sectors on a hard disk that cannot reliably store data. They can be due to a manufacturing defect, or they can develop over the disk's lifetime from physical wear, power surges, or even minor head crashes. When a sector goes bad, any data that was in that specific area is lost, and the sector becomes unusable for future storage. However, the rest of the disk usually remains functional. The crucial step is to identify and mark these bad sectors so the operating system knows to avoid them. Tools like ScanDisk and CheckDisk, or the chkdsk command with the R switch on Windows systems and bad blocks on Linux, are designed for this purpose. They scan the disk, identify these problematic areas, and then logically mark them so the OS doesn't attempt to write new data there. For an investigator, knowing about bad sectors is important because it means certain data might be genuinely irrecoverable from that specific physical location, and it's a factor to consider when assessing data integrity.
It's incredible how much data can be packed onto those platters, even with bad sectors cropping up. But how do we even begin to measure this digital universe? How do we quantify how much a disk can truly hold in a way that makes sense?
We quantify disk capacity using bits and bytes. A bit, short for binary digit, is the smallest unit of data, representing a 0 or a 1, but basically an on or off state. A byte is typically defined as a group of 8 bits. Think of it as the smallest unit of digital information that can represent a single character, like a letter, number, or symbol. While historically some systems use 7-bit bytes for all practical purposes in modern computing, a byte means 8 bits. That's why we abbreviate bit as a lowercase b and byte as an uppercase b.
Ah, good distinction. B for bit, B for byte.
Exactly. Be careful not to confuse them, as bandwidth is often in bits per second, MBPs, while storage is in bytes, MB. Because these fundamental units are so small, we use larger increments, but with a binary twist. A kilobyte, KB, perhaps surprisingly for those used to decimal numbers, isn't 1,000 bytes, but 1,024 bytes.
1024.
It's because computers use binary base 2 math. 2 to the power of 10 equals 1,024. This pattern continues. A megabyte is 1,024 KUB. A gigabyte GB is 1,024 gigabytes, and a terabyte TB is 1,024 KB. Beyond that, we have petabytes, PB, exabytes, EB, zettabytes, ZB, and even yottabytes, YB, which is just enormous amounts of data.
A yottabyte.
To give you a relatable analogy, a single terabyte can hold roughly the equivalent of 1,610 standard CDs of data, or, some estimate, all the books in a very large public library.
That's a lot of books.
It is. We can also calculate disk capacity if we know the physical parameters of the drive, which is a useful exercise for understanding storage efficiency. The general formula is capacity, byte sector, sector track surface, number of surfaces. But sometimes specifications don't give tracks per surface directly. They might give total tracks and number of heads. Since each head reads one surface, the number of heads is essentially the number of surfaces. So we can revise the formula slightly. Capacity, byte sector, sector track, total tracks, number of heads. For example, if we have 512 bytes per sector, 426 centers per track, 43,152 total tracks, and let's say 2 platters, meaning 4 surfaces or heads. The calculation would be 512 times 426 times 43,152 times 4, which equates to approximately 37.6 gigabytes. This kind of calculation helps an investigator verify stated capacities or understand storage limitations.
You briefly touched on the hard disk interface earlier, the communication channel. Given all this intricate internal organization, how exactly does the drive talk to the computer? And how have those languages evolved to affect speed and how we connect devices?
Right. The hard disk interface is indeed the critical communication channel between the HDD and the rest of the computer system. Over the years, several standards have emerged, each aiming to improve speed, reliability, and functionality. First, we had EIDE. EIDE stands for Integrated Drive Electronics, meaning the disk controller logic is built directly into the drive itself, rather than being on a separate card. EIDE, or Enhanced ID, improved upon this, and the whole family is standardized under ATA, or Advanced Technology Attachment, an ANSI standard. These interfaces typically allow 2 devices per connector, either hard drives or CD-DVD drives, configured as master or secondary, formerly slave, on a shared ribbon cable. You could set them via physical jumpers or allow the cable to control the configuration. They were common for many years, but were limited in speed and the number of devices you could connect.
Okay, IDE. I remember those ribbon cables.
Yep. Then there's SCSI, pronounced SCSI, which stands for Small Computer System Interface. This is another ANSI standard, known for its faster data transfer rates compared to early IDE and its ability to connect multiple devices in a daisy chain. SCSI controllers can be built into motherboards, but were often added via expansion cards. A key feature of SCSI is its ability to chain many devices, typically up to 7 or even 15 peripherals, depending on the SCSI version, on a single controller bus. Each device needed a unique SCSI ID. SCSI was often favored in servers and high-performance workstations for its scalability and reliability.
SCSI sounds powerful.
It was, especially back then. USB, or Universal Serial Bus, is incredibly versatile and ubiquitous today. While used for countless peripherals like keyboards, mice, and printers, it's also a common interface for external hard disks and flash drives. Its bus topology allows for daisy chaining or hubs, theoretically connecting up to 127 devices. USB has evolved through versions like USB 2.0, supporting bandwidths up to 480 megabits per second (MBPs), making external USB drives very popular for fast, portable data exchange. More recent versions like USB 3.0 and 3.1 offer even greater speeds, dramatically reducing transfer times for large files.
Yeah, USB is everywhere now.
Finally, Fibre Channel is an ANSI standard that employs optical fiber for extremely fast data transfer over longer distances. The primary standard for storage is Fibre Channel Arbitrated Loop, or FCAL, specifically designed for mass storage devices and storage area networks. SNs. SNs are specialized high-speed network architectures where multiple servers connect to shared remote storage devices like disk arrays or tape libraries, treating them almost as if they were local. Fibre channel supports transfer rates of 100 millips and significantly higher in newer iterations, and it's widely adopted in enterprise environments. It's often seen as a successor to SCSI for high-performance network storage systems due to its speed, scalability, and use of optical fiber, which is less susceptible to electromagnetic interference.
Okay, we've seen the incredible engineering inside a hard drive, how data is physically etched onto those spinning platters, and how it communicates. But imagine a library filled with millions of books, all meticulously placed on shelves, but with no catalog, no numbering system. It would be just an unusable mess.
Right. That's exactly why, once we understand the hardware, we have to talk about the unsung hero that brings order to this digital chaos, the file system.
That's a perfect analogy. File systems, also known as file management systems, are precisely the operating system's organizational backbone. Their core function is to systematically organize and locate data on a hard disk, controlling how sectors store files, tracking which sectors are used and which are empty, and ultimately making that data accessible and understandable to both the user and the applications. It truly is the Dewey Decimal System for your digital library.
Makes sense. It's important to differentiate that network file systems serve a slightly different role. They facilitate access to remote data over a network, rather than directly managing the local hard disk itself. Most file systems employ a hierarchical structure, which looks like an inverted tree. It starts with a root directory, like C on Windows or on Linux, and from there, directories or folders branch out, containing files or other subdirectories. The file system meticulously tracks this entire structure. It ensures that when you open a directory, its contents are displayed correctly, and each file can be located precisely on the physical disk. File naming has also evolved considerably. Early systems like MS-DOS imposed strict 8.3 notation. Remember document.doc? Oh yeah, 8 characters then 3. Exactly. Limiting file names to 8 characters plus a 3-character extension. Modern file systems, starting with Windows 95, enable long file names of up to 255 characters, making file organization far more intuitive. Beyond just names, file systems also manage critical file properties like the file owner, its creation time, last modified time, last access time, and various access attributes like read-only, hidden, system. For a forensic investigator, these properties and the file system structure are gold mines, providing crucial metadata about activity and intent.
Microsoft operating systems have dominated the PC landscape for decades, and with them, a series of evolving file systems. What are the key ones we need to know for forensics, and what did each bring to the table? What were the pros and cons?
Microsoft has indeed developed a fascinating progression of file systems, each addressing limitations of its predecessor. Let's trace that evolution a bit. First, FAT12, or File Allocation Table 12, was one of the earliest, developed for DOS. It used a 12-bit binary number for cluster information, meaning it could only address a limited number of clusters. It was designed for very small disks, less than 16 megabytes, MB, and you still encounter it for formatting floppy diskettes.
Floppies. Wow. Okay, FAT12.
Then came FAT16, often simply called FAT. This used 16-bit allocation table entries and became the standard for disks larger than 16 megabytes for a long time. It boasted universal compatibility, supported by nearly all Microsoft operating systems from MS-DOS to Windows XP, and even some non-Microsoft ones like OS2 and Linux. However, FAT16 had significant drawbacks, especially once hard drives started getting bigger. Imagine a 2 GB drive using massive clusters of 32 KB. You could save a tiny 1-byte text file, and it would gobble up a whole 32 KB cluster. That's thousands of bytes simply wasted, like buying a full warehouse to store a single teacup.
Right, massive waste of space.
Exactly. This poor scaling with large disks led to significant wasted space. It also didn't support file-level compression, only entire logical drive compression like drive space. And critically for forensics, it lacked file-level security. You couldn't assign permissions to individual files or folders. This made it quite vulnerable.
And no security.
Not good.
Not at all.
To address some of these limitations, VFAT, or Virtual FAT, was introduced with Windows for Workgroups 3.11 and Windows 95. It's not really a file system itself, but rather a driver or extension that enabled long file names, finally overcoming that restrictive 8.3 character limit of FAT16. It also operated in protected mode, improving stability.
Okay, so VFAT fixed the naming.
Mostly, yeah. Then FAT32 was a truly significant improvement. Introduced with Windows 95B, it used a 32-bit allocation table, drastically increasing the number of clusters it could address. This offered much more efficient space utilization with smaller cluster sizes, supported much larger partitions, theoretically up to 2 terabytes, TB, though Windows limits formatting to 32 gigabytes for backward compatibility, and it improved reliability by including a backup copy of critical data structure information in the boot record. Its main disadvantage was incompatibility with the much older operating systems like MS-DOS or early Windows 95.
So FAT32 is a big step up.
A very big step. Finally, we arrive at NTFS, the new technology file system. Released in 1993 for Windows NT and its successors like Windows 2000-2003 Server, XP, and Vista, NTFS is the most secure and robust Microsoft file system. It supports incredibly large partitions, up to 16 exabytes, EB theoretically, and features like spanning volumes across multiple physical disks. NTFS is also far more reliable due to a feature called hotfixing. Here, the OS automatically detects a bad sector, transparently relocates any data from it to a good sector, and then marks the bad sector as unusable, all without user intervention.
Hotfixing. Sounds handy.
It is. From a forensic standpoint, NTFS is a treasure trove due to its advanced metadata and logging capabilities. We'll definitely dig into that.
NTFS's reputation for robustness is almost legendary, but I always wonder how it manages to be so resilient. Most users just see files and folders, but there must be a complex, almost hidden system at play underneath. What's the secret sauce that makes NTFS so much more intelligent than its predecessors?
That secret sauce is precisely what we call metadata, and its central nervous system, the master file table, MFT. While a user sees a file, NTFS sees a collection of attributes and information about that file. Metadata is essentially data about data. Information like who created a file, when it was last accessed, its size, format, and various timestamps. This crucial information is usually hidden from the common user, but it's central to an investigator. The MFT, or MFT, is the core of NTFS. It's a special hidden system file that stores information about all files and folders on an NTFS volume in a structured way. Think of it as the ultimate index card catalog for everything on the disk.
The MFT, like a master index.
Exactly. For instance, Record 0 of the MFT describes the MFT itself. Record 1 is the MFT mirror, a crucial backup for recovery if Record 0 gets corrupted. Record 2 is the log file, a transaction log, much like a database journal, used for file system recovery and ensuring data integrity after a crash. Other records track user files, folders, and their specific attributes. Every file and directory in NTFS is considered a set of attributes. These are the fundamental properties that define the file: its name, its actual data content, and critical security information. Attributes can be resident, meaning they are small enough to fit directly within an MFT record, such as the file name itself, a timestamp, or a small amount of data. Or they can be non-resident, meaning they are too large for the MFT record and are instead allocated to clusters elsewhere on the disk, with the MFT record containing pointers to those clusters.
Resident and unresident.
Common attributes include the attribute list, which tracks where all attribute records for a file are located, bitmap for cluster allocation, data, the actual file content, file name, including both 8.3 and long names, index root allocation for directories, security descriptor containing access control lists, ACLs, ownership and auditing information, incredibly valuable for forensic analysis.
ACLs. Very important.
Absolutely. Standard information like read-only, hidden flags, and various timestamps, object ID, a volume-unique file identifier, and even volume name information version. When you, as a user, modify a file's properties, changing its name, adjusting access permissions, or even just opening it, you're directly altering these underlying NTFS attributes, creating a rich trail of forensic evidence.
That deep level of detail from the MFT sounds incredibly useful for investigations. But NTFS also has built-in features for compression and encryption. While powerful for users, I imagine these can throw a wrench into a forensic investigation, right?
They absolutely can. Yeah, they add layers of complexity that an investigator must understand. Let's look at NTFS compressed files first. This feature allows you to save space by compressing an entire volume or individual files and folders within it. The compression and decompression process is automatic and largely invisible to the user. When a program tries to open a compressed file, the file system's compression driver must first decompress it before making it available. For a forensic investigator, this means that if you're examining a compressed file outside the native operating system environment, example, directly from a disk image, you need specialized tools capable of decompressing that NTFS-specific format to access the raw data.
Right. You need the right tools.
Then there's the encrypting file system, EFS, which is integrated directly into NTFS version 5 and later found in Windows NT 2000-2003, Server, XP, Vista, and beyond. EFS provides file-level encryption, encoding files so that only authorized users can read them. This is distinct from full disk encryption. EFS protects individual files and folders on hard drives or large removable disks formatted with NTFS. Like compression, EFS is largely invisible to the user. It relies on public key cryptography. Each user has a unique public-private key pair. The private key is secret. The public key is shared. When a file is encrypted, it gets a unique file encryption key, which is itself then encrypted by the user's public key. The user's private key is then needed to decrypt the file encryption key, which in turn decrypts the actual file data. Digital certificates linked to user accounts manage this authorization.
Sounds secure, but complicated.
It is secure, but it has significant drawbacks from a forensic perspective. Sharing encrypted files securely can be difficult, and there's a security risk if a user leaves their computer logged on, as anyone sitting at the machine could access the encrypted data. More critically for us, if the user's private key is lost or unavailable, accessing that encrypted data becomes mathematically infeasible without immense computational power. This means encrypted files can present an almost insurmountable hurdle for a forensic investigator if proper key recovery mechanisms haven't been implemented or can't be bypassed.
Wow, yeah, that's a big hurdle. So while Microsoft has its dominant file systems, the digital world is far richer. What about the file systems powering Linux and Mac machines, and even those designed for massive network storage?
Good point. The landscape is definitely much broader. For Linux, an open-source Unix-based operating system, a virtual file system, VFS, acts like a universal adapter. Imagine you have a multi-region DVD player. The VFS lets Linux play or understand many different types of file systems underneath. Abstracting away the specifics of the operating system doesn't need a unique interpreter for every single one.
Like a translator.
Exactly. The earliest Linux file system was EXT, the extended file system, which replaced the limited Minix system. It was quickly superseded by X2, the second extended file system. X2 offered improved performance, support for files up to 2 TB, and using inodes, which store metadata about files and directories, and blocks, the smallest unit of data. A superblock holds critical boot information, like the total number of blocks or the location of the inode table. X3, the third extended file system, was a major improvement, introducing journaling. A journaled file system logs data changes before writing them to the main file system. This journal acts like a transaction log in a database. If the system crashes, XT3 can use its journal to quickly restore consistency without needing to run FLACSAC, file system check, for hours, which was common with X2.
Journaling, that sounds much safer.
It vastly improves data integrity and recovery speed. And then came XT4, the fourth extended file system, which further boosted performance, supports even larger volumes, up to 1 exabytes, and includes features like extent-based file storage for better large file performance. For forensic analysis, understanding the journal is critical, as it often holds clues to recent activity, even if the main file system has been corrupted.
What about Macs?
For Mac OS X, the original Macintosh, released in 1984, used the Macintosh File System, MFS, for its 400 KB floppies. MFS was quite innovative. It stored files in 2 distinct parts: a resource fork for structured info like icons, menus, and application code, and a data fork for unstructured data, like the actual text of a document. This allowed files to be opened by the correct application without needing a file extension.
Resource fork and data fork.
Yeah. In 1985, HFS, Hierarchical File System, replaced MFS, supporting hard disks and long file names up to 255 characters, and using a hierarchical catalog file structure for better performance. In 1998, HFS Plus arrived, offering even better performance and significant improvements in data handling, notably using 32-bit block addresses compared to HFS's 16-bit. This drastically reduced wasted space on larger volumes, a crucial factor for modern large drives.
Okay, HFS Plus for Macs.
And finally, for high-end enterprise storage, there's ZFS, the Zettabyte file system, originally from Sun Solaris 10. As its name implies, ZFS is designed for massive amounts of data and extreme reliability. It uses Z-pools, which are virtual storage pools composed of VDEVs, virtual devices, supporting advanced RAID configurations. ZFS is a 128-bit storage system, supports variable-size blocks up to 128 KB, and improves I/O throughput through built-in compression and data integrity features like checksumming. It's a beast of a file system designed for petabyte-scale data centers.
ZFS sounds intense. This raises an important question, though. How do all these diverse file systems, sometimes on entirely different operating systems, communicate and share data seamlessly across a network? It feels like magic, but I know it's sophisticated engineering.
It definitely feels like magic sometimes. But it's all thanks to network file systems and file sharing protocols. Their core concept is brilliant. They allow users to access and update files on remote computers as if those files were stored locally. This makes the remote machine's specific file system irrelevant to the client. A Windows 9X machine, which can't natively read NTFS, could still access NTFS files on a Windows NT server, for example.
So it hides the complexity.
Precisely. Several key protocols facilitate this. SMB, or Server Message Block, is a foundational Microsoft protocol used by client applications to access remote files and other services like printers. It's deeply integrated into Windows. SMB is an incredibly important open-source implementation of SMB for UNIX-like systems, enabling Windows clients to seamlessly access UNIX files and resources, bridging the gap between operating systems.
Samba, I've heard of that.
Then there's CIFS, or Common Internet File System, which is essentially an open, non-proprietary version of SMB, proposed as an internet standard. Both SMB and CIFS operate over the TCP/IP protocol stack, making them work reliably across the internet. NCP, the Network Core Protocol, is a set of protocols used specifically in novel networks. It provides services like file and printer access and typically runs over the IPX/SPX protocol stack, though newer versions can use TCP/IP. And finally, NFS, the Network File System, is a client-server application developed by Sun Microsystems. It runs on TCP/IP and heavily relies on RPC, remote procedure calls, to enable client computers to request services from remote servers. NFS is primarily used for remote file access by UNIX and Linux machines, but can also be installed on Windows and Macintosh computers, making it a very versatile cross-platform solution. For forensics, these protocols mean that evidence isn't just on local drives, but potentially across an entire network, requiring a different approach to acquisition.
And it's not just hard drives and networks, right? What about CDs and DVDs? Despite the rise of streaming, we still encounter them in investigations, sometimes holding crucial data.
Absolutely. Optical media have their own distinct file systems, too. UDF, or Universal Disk Format, is an industry standard for both CDs and DVDs, developed by the Optical Storage Technology Association, OSTA, and based on ISO 13346. Its goal is universal accessibility across different computer operating systems and CD/DVD players. Microsoft even released a UDF bridge with Windows 95 to ensure initial compatibility, and it's what modern Blu-rays and large DVDs use.
UDF for universal access.
Okay. Then there's ISO 9660, often called CDFS, Compact Disc File System. Introduced in 1988, is a foundational standard for CD-ROM media, ensuring cross-operating system access. Data is stored as 24-byte frames. It supports various recording modes. Mode 1 is for computer data, typically with 8.3 file names. Mode 2 Form 1 is also for computer data, allowing longer file names, up to 180 characters, but with slightly less universal compatibility. And Mode 2 Form 2 is designed for fragmented data, like video CDs, offering fault tolerance but making direct forensic recovery more complex.
Different modes adds complexity.
It does. And extensions to ISO 9660 were developed to overcome its limitations. Joliet enabled long file names, up to 64 characters, for Windows 95 and later. Apple ISO 9660 extensions provided support for Mac-specific file properties like resource and data forks. Rockridge Interchange Protocol, RIBI, was developed for UNIX-specific information, including longer file names, up to 255 characters. And El Torito is a specific extension that allows computers to boot directly from a CD. These standards and extensions help ensure compatibility and data integrity across diverse optical media applications. But for an investigator, they mean understanding which standard was used can be critical for proper data extraction.
So we have the file systems, but before they can even organize data, the physical disk itself needs to be prepared. This brings us to partitions, a seemingly simple concept with some incredibly interesting implications for forensic work.
Precisely. Disk partitioning is the logical division of a physical hard disk, allowing it to function as if it were multiple separate drives. Even if you want the entire disk as one logical drive, it still needs to be partitioned so the operating system can recognize and use it. Once a partition is set and formatted with a file system, it's assigned a drive letter, like C or D in Windows, and becomes what we call a volume. This flexibility is powerful. You could have multiple file systems on a single HBD, for instance, a FAT32 partition and an NTFS partition on the same Windows machine, or X10X2 on a Linux system, each leveraging the unique features of its file system. This is a common scenario for multi-boot systems.
Multi-boot, yeah, okay.
There are two main types of partitions. A primary partition is where an operating system can be installed and from which the computer can boot. In older systems, using the master boot record, or MBR, schema, you were limited to up to 4 primary partitions, or 3 primary and 1 extended partition. The operating system that boots usually resides on a primary partition. An extended partition, unlike a primary, cannot hold an operating system directly or be booted from. Its purpose is to act as a container that can then be subdivided into multiple logical drives. Each logical drive then gets its own drive letter and appears as a separate drive to the user, with the only real limits being the available space and the number of available drive letters. For forensics, understanding the partition layout is fundamental to know where different operating systems or user data might reside.
Speaking of booting, there's a classic point of confusion that's vital for investigators. The boot partition versus the system partition. Let's clear that up because it can often trip people up.
This is a classic point of confusion, and the names are often misleading, so let's consciously reverse our thinking a bit. The system partition is the partition that stores the files actually used to boot the computer. These are the initial files accessed during a cold or warm boot. This is where crucial elements like the MBR and the bootloader files reside. The boot partition, on the other hand, is the volume that contains the operating system files itself. Essentially, it's where the OS is installed.
Wait, say that again?
Okay, yeah, it's confusing. The system partition stores the boot files. The boot partition stores the system files. The files to start the computer are on the system partition. The files of the operating system are on the boot partition.
System partition has boot files, boot partition has system files. Wow, okay.
Exactly. They can be on the same physical volume or separate ones, but understanding their distinct, often counterintuitive roles is absolutely critical for troubleshooting boot issues or, more importantly for us, performing accurate forensic analysis and recovery. Misunderstanding this can lead to an investigator looking in the wrong place for critical boot sequence evidence.
That distinction is definitely one to remember. Now let's zoom in on the very first part of a hard disk. At the absolute beginning, Sector 0, lies something incredibly powerful, the boot sector, or master boot record. What's its critical role, and why is it such a prime target for malicious activity?
Sector 0 on any hard disk is always reserved as the boot sector. On a hard disk, this is typically where the master boot record, MBR, resides. The MBR contains two absolutely critical pieces of information. First, a small amount of executable code that starts the machine's boot process, and second, the partition table. This partition table holds all the information about how the primary partitions on the disk are organized, their starting and ending sectors, their sizes, and their type. Before the operating system even begins to load, the MBR tells the computer how to understand the disk's overall layout and which partition is active or bootable.
So it's the first step, really.
Pretty much the first piece of code run from the drive. Because the MBR takes control so incredibly early in the boot process, even before the operating system is fully loaded, it's a prime target for boot viruses. These malicious programs infect the MBR to gain control immediately upon startup, often before any antivirus software has a chance to load and protect the system. This is why you've always heard warnings about not leaving bootable media like old floppy disks in drives when starting a computer, as they could potentially contain malicious boot code.
Ah, okay, that makes sense now.
For NTFS specifically, the partition boot sector is even more crucial. It stores the exact location of the master file table, MFT, and its mirror. To protect against data loss, a duplicate of this boot sector is intelligently stored at the disk's logical center, providing a crucial recovery point if the original becomes corrupted. Compromising the MBR or boot sectors can render a system unbootable or allow an attacker to launch persistent malware.
So we have sectors, the smallest physical unit on the disk, but then we also hear about clusters. What's the fundamental difference between a sector and a cluster, and why are clusters so important for how the operating system manages files?
This is where many people get confused, but it's a truly crucial distinction for understanding data storage. A sector is, as you said, the smallest physical storage unit on a disk, typically 512 bytes. It's dictated by the hardware. A cluster, however, is a logical unit of file storage, defined by the operating system as a group of two or more consecutive sectors. It's the smallest amount of disk space that the operating system can allocate to store any part of a file.
Logical unit, yeah.
Think of it like this. Sectors are like individual bricks, but the operating system doesn't deal with individual bricks when building a file. Instead, it deals with preformed blocks of bricks. Those are the clusters. The OS manages these clusters, assigning each a unique number. While the OS tries its best to store files in contiguous clusters for faster access, reducing the read-write head movement, this isn't always possible over time. Files get created, deleted, modified, and eventually parts of a single file can be scattered across non-contiguous clusters. This is known as file fragmentation. It's largely invisible to the user but can impact performance. So remember, sectors are hardware-defined physical units, while clusters are OS-managed logical units for file storage.
Got it. Sectors physical, clusters logical. So if clusters are logical and managed by the OS, does their size actually matter in a practical sense? And can we, as users or forensic investigators, control it?
Yes, cluster size absolutely matters, and it has significant implications for both storage efficiency and forensic recovery. The cluster size is determined by the file system used and is often chosen during the formatting process. For example, in Windows XP, when you format a drive, you have an explicit allocation unit size option in the dialog box. This allows you to choose cluster sizes like 512 bytes, 1024 bytes, 2048 bytes, or 4096 bytes, 4KB. If you don't specify, Windows uses a default size based on the volume size. For instance, on Windows 2003 Server, smaller volumes often default to smaller clusters, while NTFS generally uses 4KB clusters for larger volumes. So you can choose it. Usually, yes, during format. The chosen cluster size directly impacts storage efficiency. If you have many small files on a disk with large cluster sizes, you'll waste a lot of space. Conversely, if you have very large files, larger cluster sizes can sometimes improve performance by reducing the number of allocation units the OS needs to track. It's also important to note that when converting a FAT file system to NTFS using convert.exe, the program often automatically sets the cluster size to 512 KB or sometimes 4 KB without giving you an option to change it, as FAT file systems often use larger default clusters. For an investigator, knowing the cluster size is paramount because it directly impacts where to look for slack space, which is our next crucial topic.
Ah, yes. Now we get to some really important forensic territory. Because clusters are fixed sizes, there's often leftover space that can hide crucial evidence. Let's talk about slack space. This is where digital ghosts often hide, isn't it?
Oh, slack space. This is indeed where the real digital ghosts often hide. Imagine you've got a very efficient office, but when you file a tiny note, you're forced to use an entire large cabinet drawer. The note fills only a corner, but the rest of that drawer is now used and can't be touched by other files. That leftover empty space in the drawer, that's slack space on a hard drive. More formally, it's the wasted space between the actual end of a file and the end of the last cluster allocated to that file. For example, you save a tiny 10-byte text file to a disk with a 4KB 4096 bytes cluster size. The entire 4KB cluster is allocated to that file. This means 4086 bytes are effectively wasted or unused by the current file within that cluster.
486 bytes wasted just for a 10-byte file.
Wow. Yep. Why does this happen? Because clusters are allocated entirely. Once a cluster is assigned to a file, even if the file only partially filled it, that entire cluster is considered occupied and cannot be used for other files. Smaller cluster sizes reduce this wasted slack space, which is one of the advantages of NTFS over older F8 systems. From a forensic perspective, slack space is invaluable. When files are deleted, data often remains in this slack space and also in unallocated space, which we'll get to. Even if part of a deleted file are overwritten, crucial fragments or leftover data from previous files that occupy that cluster can persist in the slack space of new files. This makes it a potential goldmine for investigators looking to recover deleted or hidden information. Any good forensic tool will meticulously examine these areas, as they can reveal surprising evidence a user thought was long gone.
A gold mine indeed. And what about when the operating system itself gets confused about which clusters are being used, leading to another form of hidden data?
That leads us to lost clusters, also known as lost allocation units or file fragments. These are clusters that the operating system has marked internally as used, but for some reason are not actually assigned to any specific file in the file system's directory structure. They're like library books that are marked checked out, but aren't actually associated with any borrower or even listed in the main catalog.
So orphaned clusters.
Kind of, yeah. They often result from improper shutdown, such as a sudden power loss, or prematurely removing storage media, like a USB drive, while data is being written. The system might have assigned a cluster for data that was in its cache, but never finished writing the full file to disk or properly updating its allocation tables. While lost clusters are often empty or contain corrupted data, they can also contain fragments of legitimate files if a write operation was interrupted midway. Tools like ScanDisk and CheckDisk in Windows, or FRAC and Linux UNX, are designed to detect and recover these. In Windows, they're often recovered as generic file, ###.cwxb files in the root directory.
Oh, I've seen those CHK files.
Yep, that's often what they are. In UNIX Linux, they're typically found in a lost plus found directory. These fragments, though possibly incomplete, can sometimes be pieced together by a skilled investigator to recover valuable missing data that might be crucial to an investigation, giving context to activity or reconstructing deleted information.
To bring this all together, let's look at a concrete example, the core files that make up Windows XP and how they boot a system. This helps us understand what an attacker might target or what we need to recover if a system is compromised.
Understanding these core Windows XP files is absolutely vital for an investigator. Think of them as the critical organs of the operating system. The fundamental components of Windows XP, residing mostly in %system root %system32, include endocase krnl.exe. This is the executive and kernel, the very brain of Windows, handling core tasks like memory management, process management, and hardware virtualization. If you find any unauthorized modifications or unfamiliar versions of this file, it's a huge red flag for a rootkit or deep system compromise.
The kernel, definitely critical.
And ntkrnlpa.exe. This is specifically for physical address extension, PAE support, allowing the system to access over 4 GB of memory. HAL.dll, the hardware abstraction layer. This acts as the translator between the OS and the underlying hardware. If an attacker wants to hide their tracks from the operating system, they might target files like these to trick the OS about the true state of the hardware. Win32k.sys, the kernel mode Win32 subsystem, crucial for graphical output, GDI. ntdll.dll provides internal support functions for the NT layer. Kernel32.dll manages core Windows functions like memory, I/O, and interrupts. advapi32.dll provides advanced API services, security functions, and registry calls. User32.dll implements the Windows User API for user interface elements. And GDI32.dll manages graphics device interface GDI functions for drawing graphics.
Okay, a whole team of core files. Exactly. Beyond these core components, specific startup files are located in the root directory, for example. These are crucial for the boot sequence. NT-LDR, the NT loader. This is the first significant program loaded. It reads the boot.ini file and loads the kernel components, boot.ini, a text file containing OS startup options allowing you to choose between different operating systems or boot configurations. Tampering here can redirect the boot process, nttech.com. Queries the system for device information during startup, pagefile.ildes, the virtual memory swap file. This often contains data from RAM, including fragments of sensitive information even after a system shutdown, making it forensically valuable.
Page file. Interesting.
Very. And ntbootdd.sys, used specifically for SCSI disk access instead of the standard boot code if SCSI devices are present. Knowing their normal functions tells us what's abnormal and where to look for signs of intrusion or misconfiguration.
That's a lot of critical pieces. So what does this all mean? How do all these specific files and components actually come together step by step when you hit the power button to boot up a computer? It's a precisely choreographed sequence, like a digital ballet. Here's the simplified breakdown of the boot process. Step 1. Power on self-test. Post. When you hit the power button, the computer first performs a post. This checks essential hardware components like memory, subsystems, and any BIOS-recognized devices. Step 2. BIOS reads MBR. Assuming post is successful, the computer's BIOS, basic input-output system, then reads the master boot record, MBR, from sector 0 of the designated boot hard disk. Step 3. MBR takes over. The MBR then takes control, referencing its partition table to identify the active bootable partition and loading its boot sector. Step 4. NTLDR loads. For Windows XP, the NT loader NTLDR is then loaded and executed. NTLDR reads the boot.ini file, if present, to display boot options, and then loads essential kernel components like ntskrnl.exe takes over, starting critical processes like winlogan.exe, which it loads lsas.exe, Local Security Authority Subsystem Service, to display the familiar login screen.
Okay, POST, BIOS, MBR, NTLDR, kernel. Got it.
For older operating systems, or in cases of system corruption, boot disks were and still can be invaluable. These are bootable floppies or CDs containing the essential files needed to start the computer, often obtained from specialized sites like bootdisk.com. They allow you to get a system running, even if its main operating system files are damaged, which can be a lifeline for initial forensic triage. Beyond the core files, Windows has another massive repository of information, essentially its brain, that records almost everything. That's the registry. How does this central database function, and why is it so incredibly important for forensic analysis? The Windows registry is exactly that, a central hierarchical database where critical system, application configuration, and initialization information is meticulously stored. This includes everything from hardware details and operating system settings to installed software, user preferences, network configurations, and file associations. Any changes you make via the control panel, installing software, or even just modifying Windows Explorer settings are ultimately reflected and stored here. You can even modify it directly using the registry editor. Regedit.
Regedit.use with caution.
Absolutely. The registry is organized into main groups called hive keys, often abbreviated as HKeys. These include HKey classes root, stores information about registered applications and file associations, telling Windows which program opens which file type. HKey currentisor contains configuration information specific to the currently logged on user. HKey local machine holds settings that are common to all users on that computer, including hardware and software configurations. HKey users contains individual settings for each user account that has ever logged onto the system. HKey current config. This is a dynamic hive containing information compiled each time the computer boots, reflecting the current hardware profile. It's not permanently stored.
Okay, the main HKeys.
Each HKey contains further subkeys, which are structured much like directories, and these subkeys then contain values. These values are the actual data entries, which can be of different types, such as string, binary, or duword, double word, a 32-bit number. For a forensic investigator, the registry is an incredibly rich source of evidence, revealing user activities, installed programs, connected devices, via USB history, for example, system configurations, recently opened documents, and even evidence of malware persistence. It's often the first place an investigator looks after imaging a drive.
Understanding all these intricate details of disks, file systems, and the OS itself is vital because it tells us where to look. But once we've identified potential evidence, how does an investigator actually access and analyze that incredibly granular data, especially the hidden stuff like slack space or deleted fragments? What are the workhorse tools that bring this invisible evidence to light?
That's where specialized forensic software becomes your absolute best friend. These tools are fundamental for acquiring, duplicating, recovering, and analyzing data, often in a forensically sound manner, meaning they don't alter the original evidence. Take WinHex, for example. It's not just a hexadecimal editor, it's a low-level data explorer. When you're looking for remnants of a deleted file or trying to understand what's lurking in slack space, WinHex can bypass the file system entirely. It reads the raw bytes directly from the disk platters, allowing you to manually piece together fragments or spot patterns the operating system has long forgotten. It's like having X-ray vision for your hard drive.
X-ray vision, I like that.
If you lack the native application to open a file or it's corrupted, WinHex allows you to view its raw contents and sometimes extract key information. It's also useful for analyzing network packet captures to find embedded data like passwords. Crucially, WinHex offers a disk cloning feature to create exact bit-for-bit duplicates of hard disks for analysis, preserving the original evidence. It also has a RAM editor to access physical RAM and virtual memory processes, capturing volatile data that might not yet be saved to disk. A key feature for forensic work is its write-protected mode. This opens files and disks as read-only, preventing any accidental or intentional modification essential for maintaining evidence integrity.
Write protection,
Yeah.
absolutely key.
Definitely. Another example is Evidor, the evidence collector. This tool focuses on searching hard disks for textual keywords, which is incredibly useful. It can find these keywords even within slack space and deleted data, which are often overlooked areas. It generates an output file, usually in HTML or plain text, containing only the results matching your keywords. This helps to avoid displaying unrelated confidential information. This targeted approach makes it very efficient for specific intelligence gathering. These tools, and others like them, leverage our understanding of sectors, clusters, MFT, and slack space to go beyond what the operating system presents to the user, revealing the true state of the data on the media.
It's easy to get fixated on the hard drive, especially after that deep dive, but data lives everywhere, from old-school magnetic tapes to modern flash drives and even smart devices. What are the other crucial digital media devices we encounter in investigations?
That's an excellent point. The scope of digital media is vast. First, let's clarify an important distinction. Removable media refers to cases where the disk, tape, or card itself is removed, while the drive component, the reader-writer, stays attached to the computer. This is different from removable disk drives, where the entire drive unit, like an external USB hard disk, is removed from the computer. This distinction is important in forensics as it affects how the media is handled and the chain of custody.
Media versus drive. Okay.
Let's take a trip down memory lane. Magnetic tape was one of the earliest methods for storing digital data, used extensively from the 1950s to the 1970s with large 10.5-inch reels, and later in the 1980s with audio cassettes for home computers. Today, it's still used as an inexpensive, high-capacity backup solution for servers and individual PCs, especially for archival purposes. However, magnetic tape is a sequential access medium, meaning you have to wind through the tape from the beginning to find specific data. To get to file 20, you must pass through files 1 through 19.
Like an old cassette tape.
Exactly. This makes it less practical for frequent random access compared to direct access media like hard disks. Floppy diskettes also have a rich history, evolving from 8-inch to 5.25-inch, and finally, to the familiar 3.5-inch format. These consist of a flexible plastic disc coated with magnetic material, housed in a rigid plastic case. Drive heads, which are tiny electromagnets, read and write to the disc as it spins. Standard 3.5-inch diskettes hold 1.44 MB, though technologies like SuperDisk offer higher capacities of 120 MB or 240 MB. While largely obsolete for primary storage, they still appear in legacy systems or as a means of transferring small files in isolated environments. For forensics, recovering data from old, physically degraded floppies can be a real challenge.
Then came optical media, revolutionized by lasers and pits. CDs and DVDs are still very much a part of our digital landscape. What's their unique story, and what makes them different from magnetic media?
CDs and DVDs are fascinating because they are optical media. Instead of relying on magnetic patterns, data is burned onto a photosensitive or metallic coating as incredibly tiny pits or bumps, which are then read and written by a laser beam and an optoelectronic sensor. DVDs use similar technology but store significantly more data, typically 4.5 EB to 17 GB data compared to 700 millibeats for CDs. Due to smaller pits and tracks, more efficient error correction, and the ability to have dual layers of data.
More data, smaller pits.
Right. Crucially, both CDs and DVDs are electro-optical devices, meaning they are inherently immune to magnetic fields. This is a critical distinction from magnetic floppies or hard drives, which can be affected by strong magnetic fields. This also means they are unaffected by electromagnetic pulse, EMP effects. However, they have their own sensitivities. They are sensitive to heat, above 120 degrees Fahrenheit, and recordable disks, which are written by creating marks with heat, are sensitive to infrared, IR, and ultraviolet UV light. Certain EEPROM erasers that use intense UV light can even affect rewritable media, a critical consideration for forensic handling, as alternative light sources used to illuminate latent prints, for example, could inadvertently damage or alter the evidence.
Wow, light sources could damage them. Good to know.
Definitely. Data on CDs and DVDs is organized in a single long spiral pattern, read and written from the inside out, which is the opposite of how hard drives work with their concentric tracks. A standard CD spiral is over 3.7 miles long, and a dual-layer DVDs is an astonishing 7.8 miles.
Miles long. Incredible.
Their construction varies. A CDR, compact disc recordable, has a die layer that can be written to only once, making it a worm, write once, read many, medium. A CD-ROM, compact disc read-only memory, has information manufactured directly into a reflector layer with no die layer. A CBRW, compact disc rewritable, replaces the die with metallic alloys that can change states, allowing it to be rewritten many times, typically around 1,000 times. DVDs are constructed by bonding two half-thickness discs with information layers 0.6 millimeters from the surface. In terms of durability, the thick polycarbonate bottom layer of a CD helps protect against minor scratches as they are out of focus for the laser. However, the top lacquer layer is often quite thin, and a scratch there can damage the crucial reflector layer, rendering the disc unreadable. DVDs are generally more robust as they often have polycarbonate on both sides, making it harder to scratch the critical information layer.
What's fascinating here is that even within CDs and DVDs, there's a whole family tree of different types, each with its own capabilities and, more importantly for us, forensic implications.
That's right, the array of optical media can be quite diverse. For CDs, we have CD audio, CDVA, the original format for music, designed for widespread compatibility with its physics largely unchanged since 1980, and CD-ROM, compact disc read-only memory. These are data CDs capable of holding up to 700 millibit and still a very common method for software distribution, backups, and archival.
CDGA and CD-ROM. Simple enough.
For DVDs, originally known as digital video disc or digital versatile disc, their capacity ranges significantly from 4.5 GB single-layer, single-sided, to a massive 17 GB dual-layer, double-sided. The various types include DVD-R, minus recordable, a 4.5 GB write, once read, many, worm, medium. Once data is written, it cannot be modified, which makes them excellent for preserving evidence as they guarantee non-alteration. They often have better compatibility with consumer DVD recorders for data files.
Worm. That's forensically sound.
It's exactly DVD plus R plus recordable. Also, 4.5 GB, similar in function to DVD-R, but using a slightly different recording method. Some older players only read plus R discs. DVD-RW, minus read-write. 4.5 GB, recordable and rewritable, allowing around 1,000 writes. DVD plus RDL, dual layer. An extension supporting dual layer recording, boosting capacity to 8.5 GB. Most current drives support reading and writing these. DVQ plus RW plus read-write, 4.5 GB, recordable and rewritable, also allowing around 1,000 writes. DVD RAM. An older, now largely obsolete format that emphasized extreme rewritability, over 10,000 writes, but faced significant interoperability issues, limiting its adoption. For forensic purposes, understanding whether a disk is worm media, like DVD or CDR, is absolutely crucial, as it fundamentally impacts the integrity and admissibility of the evidence. A worm disk ensures that once data is written, it cannot be tampered with.
The race for higher definition really pushed the boundaries of optical storage, bringing us new formats that were briefly in competition. What were HD, DVD, and Blu-ray all about, and how did that format war play out?
That was a significant format war, wasn't it? One that captivated tech enthusiasts for years. On one side, we had HD DVD, high-definition DVD, primarily developed by Toshiba and NEC. It was designed as a high-density successor to DVD, specifically for high-definition video content. A single-layer HD DVD could store 15 GB and dual-layer discs up to 30 GB. They were designed for HDTV resolutions and offered impressive 36 mm transfer rates. Its main competitor was Blu-ray. The name comes from the blue-violet laser used to read and write to the discs, which has a shorter wavelength than the red lasers used in CDs and DVDs, allowing for much finer focus and thus more data density. Blu-ray offered even higher capacities, 25 GB for single-layer and a massive 50 GB for dual-layer discs.
Blu-ray won that one, right?
It did. Both formats were used for high-definition video and data storage, and for a while, consumers had to choose between players for one format or the other, though combination drives eventually appeared. Ultimately, Blu-ray emerged as the dominant format, thanks in part to strategic backing from major Hollywood studios and the gaming industry, particularly Sony's PlayStation 3. From a forensic perspective, both represent potential sources of high-volume data in specific cases.
Okay, so we've covered the big fixed disks and the optical ones. But what about the devices we carry in our pockets, the truly portable digital media? These are increasingly crucial for forensic investigations, often holding a snapshot of a person's digital life.
You're absolutely right. Portable media players and flash drives have become treasure troves for investigators. Let's start with portable media players. iPod, developed by Apple, revolutionized portable media back in 2001. While initially for audio, video capabilities were added, and variations like the full-size iPod Classic used tiny internal hard disks, while the Nano and Shuffle primarily used flash memory. For forensics, iPods are highly relevant because, beyond just music and videos, they can store photos, calendars, contacts, and any other type of file. The Enable Disk Use option in iTunes activates this, turning the iPod into a generic storage device. Files are often stored in hidden folders, requiring investigators to enable viewing of hidden files. The file system used depends on the formatting computer. FAT32 for Windows, HFS Plus for Mac, with the iPod Shuffle being an exception, using only FAT32.
So an iPod could just be a hidden hard drive?
Essentially, yes. Zune, Microsoft's portable media player launched in 2006, offered audio, video, image storage, and even unique features like wireless file sharing between Zunes. It could connect to an Xbox via USB. Despite being a Microsoft product, it initially had compatibility issues with Windows Vista until late 2006. Like iPods, they represent potential sources of diverse digital evidence, including communications, personal data, and media content.
Flash memory really has become ubiquitous, from tiny cards to the USB drives we all carry. It's almost become the default for quick data transfer. But what exactly makes these devices unique, especially from a forensic standpoint?
Flash memory is indeed ubiquitous and critically important. Flash memory cards are incredibly popular for storing and transferring data, with capacities ranging from a few megabytes up to hundreds of gigabytes or more now. They are non-volatile, retaining data without power, unlike RAM, making them ideal for digital cameras, photos, videos, handheld computers, programs, data, and increasingly embedded systems. Common types include secure digital SD, compact flash CF, memory stick MS, multimedia card MMC, XD picture card XD, and smart media SM. They typically require specific readers or writers to interface with a computer.
So many card types.
Tell me about it. USB flash drives, often called thumb drives, pen drives, or jump drives, are small, highly portable, removable, and rewritable storage devices that connect directly via a standard USB interface. Capacities have soared, ranging from 32 MB way back when to well over a terabyte now. They consist of a tiny circuit board in a plastic or metal casing, with the USB male connector, often with a cap for protection. From a forensic standpoint, several features of USB flash drives are particularly noteworthy. Many, especially older ones, have a small write protection switch. This is invaluable because it physically prevents any modification, deletion, or addition of data, allowing an investigator to analyze the drive in a truly read-only state, preserving its integrity for evidence.
That little switch is gold.
It really is. Many also come with built-in software for encryption, compression, or even portable applications like web browsers or office suites. These portable applications can be configured to store their history, temporary files, and user data directly on the flash drive, making it harder to track browsing habits or activities if the drive is removed from a host computer. And their small size and commonality mean they can be disguised in everyday objects, like pens or watches, which can make them difficult to identify without close inspection. The sheer volume and portability of these devices make them a common source of critical evidence in almost any digital investigation.
So we've covered the vast landscape of data storage. Now, with all these ways to store data, one type stands out in forensic investigations for its sheer volume and frequent relevance: image files. We're talking pictures, graphics, everything visual. Why are these so often central to a case?
Image files are incredibly important in forensics due to their sheer ubiquity and the immediate, often impactful nature of visual evidence. The internet and modern computers are inherently graphical, leading to thousands, sometimes millions, of image files on any given system. From operating system graphics and software icons to temporary internet files, user photos imported from cameras, downloaded images, or shared content. While many are innocuous, a significant portion can be highly relevant to an investigation, directly illustrating activities or intent. Consider, for example, cases involving illicit content. Now, the source material provides some statistics here for context on why image searches are common. For example, it mentions significant spending on internet pornography and the distribution percentages of child pornography online. As impartial reporters, we note these statistics purely to illustrate the prevalence cited in the material and why investigators often need to examine image files. Possession of child pornography is, of course, a severe criminal offense, and even possessing adult pornography on a business computer can lead to disciplinary actions. These realities underscore why forensic investigators must be proficient in locating, recovering, and analyzing image files, as they often provide undeniable proof of activity.
Right. It's about understanding the context of why these searches happen. So images aren't all created equal, are they? There are fundamentally different ways a digital picture is made, which profoundly affects its quality, its file size, and crucially for us, how we analyze it forensically. Can you break down these graphic types for us?
Exactly. We can classify graphics into three main types based on their creation and structure. First, and most common, are raster images, also known as bitmapped images. These are created or captured as a set of individual pixels, short for picture elements, mapped to a grid of X and Y coordinates. Each pixel is a tiny dot that contains programmable information defining its color, size, and location. The term raster actually comes from the Latin rastrum, rake, describing how the image is rendered pixel by pixel, much like how an image slowly loads line by line on an old screen.
Raster, like scanning line by line.
Precisely. Raster images are measured by their pixel count, for example, 640 by 480 pixels, and their resolution, which is their sharpness, typically measured in dots per inch, dpi. Higher dpi means more pixels per inch, resulting in a higher, crisper resolution. For example, 71 dpi is low for web, 300 plus dpi is high for print. A critical point for forensics is that resizing a raster image doesn't change its inherent resolution. Enlarging it simply makes the existing pixels larger and more visible, leading to jagged, blocky edges which can reveal manipulation.
Pixelation.
Yeah, it's exactly. Color depth is also vital, measured in bits per pixel, BPP. This determines the number of colors an image can display. 8-bit color gives 256 colors, 16-bit high color gives about 65,000, and 24-bit true color provides a vast 16 million colors, using combinations of red, green, and blue, RGB. Second, we have vector images. These are fundamentally different. Instead of pixels, vector images are generated from mathematical information that defines shapes like circles, squares, lines, and curves as independent objects. Programs like Adobe Illustrator, CorelDRAW, or CAD, computer-aided design programs, create these. The huge advantage of vector images is that they don't lose resolution when enlarged or reduced. A company logo, for example, can be scaled perfectly from a tiny icon on a business card to a massive billboard without any pixelation or loss of sharpness. This is because the software recalculates the mathematical definitions for the new size.
Infinitely scalable.
Pretty much. Eventually, vector images are often rasterized, converted into pixels for display on screens or for printing on devices that only understand pixels. Scalable Vector Graphics, SVG, is an XML-based specification allowing vector graphics on web pages that are portable, resizable, and can even be interactive.
For forensics, finding original vector files can be significant as they represent source material that has not undergone the degradation of rasterization or lossy compression. Third, there are metafile graphics. These are a hybrid combining aspects of both raster, vector, and even type data. They also share the advantage of vector images in being enlarged or reduced without resolution loss, making them versatile. Examples include encapsulated PostScript, DBIS, computer graphics metafile, .cgm, Windows metafile.wf, and enhanced metafile.emf. These are often used in desktop publishing or for embedding graphics that need to scale well.
Okay, raster, vector, and metafile. So, given these different types, what does this all mean for the actual image files we commonly find on computers? There's a bewildering array of file formats. Which ones are key for us to recognize and understand, and what are their forensic quirks?
For raster graphics, which are what you'll encounter most frequently, there are several key formats. BMP bitmap files are uncompressed bitmapped images, used extensively in Windows and OS/2 for system graphics, wallpaper, and scanned images. They support 24-bit color, 16.7 million colors. Because they're uncompressed, they're often very large files, making them generally not ideal for the internet, though browsers like Internet Explorer do support them. For an investigator, the uncompressed nature means they often contain a pristine pixel-by-pixel representation, which can be valuable. However, you shouldn't dismiss BMP files as just system files without analysis, as users can easily create or save evidence in this format.
Big but pure data.
Right. GIF graphics interchange format, developed by CompuServe, uses an 8-bit palette, limiting it to 256 colors. This makes it ideal for line art, cartoons, and logos that don't require high detail or a wide color range. Key features include interlacing, progressive encoding, where the image appears fuzzy then clearer as it loads, like Venetian blinds, and transparency, where one color becomes invisible, letting the background show through. GIF89A also added support for animation, displaying individual frames in sequence, and importantly, can contain hidden textual comments within the file, which can be a forensic discovery.
Hidden comments in GIF. It's interesting.
Definitely something to look for. PNG, Portable Network Graphics, was developed as an open-source successor to GIF, largely to avoid licensing issues and to offer significant improvements. It supports 24-bit color, full alpha channel transparency, much more sophisticated than GIF's simple transparency, interlacing, and various powerful lossless compression methods. Notably, PNG itself does not support animation. Its companion format is MNG, but it's now widely supported by all major internet browsers and is a versatile format. JPEG, Joint Photographic Experts Group, is the most popular image format on the internet, named after the committee that developed it. It supports 24-bit color and, crucially, uses lossy compression to create much smaller files. This combination of good color depth and manageable size makes it perfect for transmitting detailed photographic images over the internet. It also supports progressive JPEG, which is its form of interlacing. For forensics, the lossy compression is a critical consideration, as it means data is permanently discarded, impacting image quality, especially with repeated saves.
Lossy, so data is lost forever.
Yep. JPEG 2000 is the successor to the original JPEG, offering the same features plus transparency and improved compression that results in less quality loss compared to the original JPEG at similar file sizes. It's used in digital cameras, medical imaging, and various software. TIFF, Tagged Image File Format, is a very common format for professional print, desktop publishing, and graphic design, originally created for scanned images. It offers a wide color range, 8, 16, 24, 32-bit, and produces very high-quality images. Consequently, TIFF file sizes are often large. TIFFs are generally not natively supported by internet browsers, but are used by many digital cameras for high-quality, uncompressed, or losslessly compressed images. The format's flexibility means it can contain various compression types within it.
Because image files, especially high-resolution ones, can be absolutely huge, compression is crucial for storage and transmission. But there's a big distinction that's vital for forensic work: lossy versus lossless compression. Can you explain the difference and its implications for investigators?
Understanding data compression is indeed critical, especially when evaluating image integrity and potential evidence. The primary purpose of compression is to reduce file size by eliminating redundant information. There are two fundamentally different methods. Lossy compression works by eliminating data from the file, thereby sacrificing some image quality to achieve a much smaller file size. The compression algorithm deems certain data expendable because it believes the human eye won't notice its absence significantly. While often unnoticeable initially, the image degrades with multiple saves. For instance, repeatedly saving a JPEG, which uses lossy compression, will eventually lead to visible artifacts, blockiness, and a permanent loss of detail.
Imagine trying to make a perfectly clear photocopy of a photocopy of a photocopy. Eventually, you lose resolution. This degradation can be a forensic clue if an image has been repeatedly saved.
Okay, lossy degrades over time.
Techniques include chroma subsampling, which reduces color info more aggressively than brightness, leveraging the human eye's greater sensitivity to luminance. Color reduction decreases the total number of colors used. Fractal compression identifies and duplicates similar parts. Transform coding averages colors. And vector quantization approximates data with a smaller, predefined set of values. In contrast, lossless compression reduces file size without sacrificing any image quality. No original data is permanently lost. The original data can be perfectly reconstructed upon decompression, bit for bit. Because all data is preserved, the compression ratio is generally lower than with lossy methods, typically a maximum of 50%. This is like zipping a document, you get the exact original back.
Lossless means perfect reconstruction.
Exactly. Techniques include adaptive dictionary algorithms, like LZW, used by GIFs and TIFFs, which find common elements and replace them with shorter codes. Deflation, a combination of Huffman coding and LZ77 coding used by PNG, MNG, TIFF, and ZK files. LZ77 finds repeated sequences. Huffman assigns shortest codes to frequent patterns. Entropy encoding, like Huffman coding, also looks for patterns and replaces frequent ones with smaller codes. And one-length encoding finds repetitive sequences and stores them as a count, plus the value, like AAAABBC becomes 5A2B1C. The crucial takeaway for forensics is that lossless compression guarantees exact data preservation, making the image a perfect representation of the original source. Lossy compression, however, introduces irreversible changes, which can be important for detecting manipulation or understanding image provenance.
So we know what images are and how they're stored, but how do investigators actually find them, especially when they're damaged or hidden, and then ultimately present them as evidence in a clear, defensible way?
Locating and recovering image files is a common and often high-stakes task in digital forensics, frequently involving hard disks, DVDs, CDs, and other large media. A key aspect is understanding image file headers. These are initial portions of a file containing critical metadata like the image's size, resolution, and color depth, along with unique magic numbers or characters that identify the file type, example BM for BMP files, FFD8 for JPEGs. Forensic tools rely heavily on these headers to determine if an image is intact and can be opened. If a header is missing or damaged, perhaps due to a partial overwrite or corrupted file system, the file may appear corrupted or not open at all. While manually restoring a header from another file of the same type is sometimes possible, it's a delicate operation and can lead to distorted or unrecognizable images if the information, like height and width, is incorrect.
Headers are like the file's ID card.
Pretty much. Even when files are deleted, parts of the data can persist as file fragments in unallocated space or slack space. These fragments can often be viewed and sometimes partially reconstructed using a hexadecimal editor, even if not to their exact original state, enough to discern critical content. This process is generally more complex for highly compressed image formats than for simpler text files, but it's a vital technique for recovering seemingly lost visual evidence. Sometimes, investigators encounter unknown files with unfamiliar extensions or no associated programs. Resources like FileX, www.filex.com, are invaluable here. You can input an extension and get information about the file's name, its likely function, e.g. graphic, executable, document. Important notes, e.g. .spvr is often a renamed .rar file. It's MIME type, proprietary company, identifying characters, those header data points, and links to associated programs. This helps quickly identify and potentially open files that might otherwise be overlooked.
This raises an important question. What specialized tools do forensic professionals use to handle this unique challenge of image files, especially when preserving their integrity is paramount?
Specialized tools are absolutely essential, as modifying evidence, even accidentally, can compromise an entire case. General forensic software like EnCase is a workhorse. It can create bitstream images, exact duplicates, bit for bit, of hard disks, including deleted files and data in slack space, and often includes built-in viewers for photos and graphics, allowing for preliminary examination within a forensically sound environment.
EnCase, a standard tool.
Very much so. More specific tools include GFE Self, Graphics File Extractor. This tool is designed to work with safe-back bitstream backup files, which are often used by agencies like the FBI and IRS for data acquisition. GFE Stealth extracts photos and images directly from these bitstream copies without any compression or translation, preserving the original data and ensuring its integrity. P2 Explorer. This allows investigators to view and browse images created with tools like SafeBack, EnCase, or Parabin's Forensic Replicator after mounting them. It lets you examine acquired data in a user-friendly manner. iLook. This provides a graphical user interface, GUI, similar to Windows Explorer, allowing investigators to examine directory structures, extract files, and includes built-in hex viewing and reporting features.
Okay, some specific extractors and viewers.
Now, for non-forensic personnel like law enforcement officers, lawyers, or employers who need to review evidence, picture viewers are often used. Examples include IrfanView, ACDC, and XinView. These tools are much simpler to use, showing directories, image previews, properties, and even valuable AXEF data, exchangeable image file format. AKF can reveal camera type, exposure settings, GPS coordinates, and the exact date and time a photo was taken, critical metadata.
XNF data. Super useful.
Incredibly. However, and this is a crucial warning for any investigator, most common picture viewers can modify images, even if just by updating the last access timestamp when the file is opened. This seemingly innocuous change can compromise evidence credibility in court. The best practice when providing copies of images for non-forensic personnel to view is to store them on DVD-R or CDR worm disks. Remember, worm means write once, read many, which physically prevents any accidental modification, thereby preserving evidentiary integrity. You literally can't overwrite them.
Worm media for sharing evidence. Got it. Beyond just finding images, what's fascinating here is how images can also be used as containers to hide other data, a technique called steganography. This sounds like something out of a spy novel.
It absolutely is, and it's a significant challenge for investigators. Steganography is the process of hiding one form of data, like a secret message, a file, or even an entire program, within another seemingly innocuous form of data, often an image file. The goal is to conceal the very existence of the hidden communication.
Hiding in plain sight.
Exactly. The mechanism typically involves using the unused or least significant bits within the image file bits that don't visibly affect the image itself. For example, in a 24-bit color image, changing the very last bit of a pixel's color value will result in a change too subtle for the human eye to perceive. A secret message can be broken up, encrypted, and then stored across these seemingly insignificant bits throughout the image. To the casual observer, the container file, the original image, looks completely normal and innocent. The hidden information usually requires specialized software, often the same program used to embed it, to retrieve and decrypt it. Steganography can also take other forms, such as hidden digital watermarks. This technique is a significant challenge for forensic investigators, as detecting hidden data can be extremely difficult without specific tools and knowledge, and often involves statistical analysis or comparing image hashes to known originals. We'll delve into the specifics of steganography detection in much more detail in Chapter 7.
Finally, when dealing with images, especially those found in an investigation, there's always a legal overlay that we must consider: copyright. It's a fundamental right that can often be overlooked in the digital age.
Copyright is indeed a fundamental form of legal protection that prevents the unauthorized use and copying of a person's original work, and this absolutely extends to photographs, logos, graphics, and other visual media. For instance, a professional photographer owns the copyright to their photos, even if a client pays for prints or digital copies. The photographer has the exclusive right to reproduce, sell, display, or create derivative works from those images. This means simply downloading an image from the internet and reusing it without permission can be a copyright infringement.
Right, you can't just grab images.
In the U.S., copyright protection has been automatic since 1989. As soon as a photograph or graphic is created in a tangible form, it is protected. While not required, registering a work with the U.S. Copyright Office, www.copyright.gov, provides official proof of creation date, which can be invaluable in civil litigation if copyright is violated. Laws vary internationally but are often enforced through treaties. Understanding these nuances is crucial because the illicit use or distribution of copyrighted material can itself be a part of an investigation or lead to separate legal actions. For example, in cases of corporate espionage, unauthorized use of proprietary images or designs could be a key piece of evidence. #outro.
Wow, what a journey. I mean, from the spinning platters of a hard drive to the hidden messages in a picture, we've truly taken a deep dive into the systems, disks, and media that form the foundational backbone of our digital world. We've explored how understanding minute details like form factors, the intricate workings of file systems like NTFS and its powerful MFT, and even the unique quirks of flash drives are absolutely essential for any forensic investigator.
If we connect all this to the bigger picture, it's clear that a mastery of these concepts is just non-negotiable for anyone in digital forensics. Knowing about slack space, lost clusters, the specific attributes within an MFT, or even the different types of image compression isn't just academic, It's precisely where crucial evidence is found or, regrettably, overlooked. And understanding subtle differences, like the right protection on a USB drive or the worm nature of a DVD-R, can truly make or break a case's integrity and admissibility. These are the fundamental building blocks upon which all successful digital forensic investigations rely.
So as you go forward, maybe consider this. Given how much data exists in hidden areas like slack space, lost clusters, or even within the depths of the Windows registry, what implications does this persistent digital footprint have for personal data privacy, even long after someone thinks they've deleted everything? It's a thought that certainly changes how you view a simple, empty trash command. That's all for this deep dive. Thank you for joining us on this essential exploration of digital foundations. Until next time, keep digging.